Okay, thank you, Jean. Hello, everybody. Thank you for joining what I'm sure is another in a long line of Zoom sessions for you today. So I really appreciate your being here with me, despite it not being in person. So I am going to present to you today some work that I've been doing with students, postdocs, others in biostat, and clinical collaborators at University of Pennsylvania. I'm trying to think through whether or not there are better approaches that we could be using to address some of the challenges that we encounter in the analysis of electronic health records data. So in particular, on this first slide, I want to make sure that I acknowledge the contributions of Kylie Getz and Dan Vader. In particular, Kylie is a former student of mine. Dan is my current postdoc. And so the work that I'm going to be presenting today is really their work. I give credit for everything that is smart and good to them, and all errors you can blame on me. So most of my research focuses on how we can use electronic health records to try to make valid inference about what's going on with people's health and healthcare and utilization and outcomes. In general, I think this is a really interesting question because EHR data present us with a huge amount of information. There's a huge wealth of data there. And so it's very natural to think, how can we leverage this data? How can we harness this information in order to learn more or faster or better than what we're able to do with traditional designed observational studies with primary data collection? However, because EHR data exist for the purposes of supporting clinical care and the administration and billing of clinical care, they have a lot of features that from a research perspective are not ideal. So most of my research focuses on how can we deal with those non-ideal features of EHR data in order to make valid inference. On this slide, I have a figure from Google Labs that illustrates the process of a single patient interacting with the healthcare system with a single EHR. So this is one patient. We see this patient over time. They sporadically engage in care. That care takes different forms. In this case, we see a patient who sometimes has primary care visits. Later in time, they have a hospitalization. And at each of these encounters, so at each point in time where the patient touches the healthcare system, based on the specific health situation of that patient and their clinical needs and the judgment of their provider, they're going to experience a different set of tests being performed, codes recorded, prescriptions made, procedures performed, and so on. So if we were to take this data and put it into an analytic database type of a form, what it would look like superficially is standard longitudinal observational data where we have repeated measures over time for a patient. And at each visit where the patient is touching the system, we have a whole bunch of variables that potentially could have been recorded. But at any given visit, only a subset of those are actually going to be populated based on the tests that the patient actually received at that point in time. So if we take this patient's data and we stack it together with 100,000 other patients who also participated in our healthcare system, we end up with an EHR database, which does look superficially like a standard longitudinal observational database, except there's going to be a high degree of missingness because each patient is going to differ in which specific tests they had performed. And it's going to be extremely heterogeneous across patients, the depth of information that we have. So some patients may, like this one, have dozens of visits and tons of different tests recorded. Other patients may have only one or a few visits and very little information. So we're going to have a data set that is characterized by high heterogeneity between patients and by a lot of missing data. And in particular, the structure of that missingness is going to be pretty complex in that it's driven by the health needs of the patient and their healthcare access, their health literacy, and how they choose to interact with the system. So overall, it's a pretty complex and messy kind of a structure. And it's generally pretty undesirable from the perspective of standard statistical approaches, because we typically would like to assume that the data that are collected conform to some kind of pre-specified protocol that consists of the visit schedule and the types of measures that we need in order to conduct research. So if we have a particular clinical question, we would typically specify a frequency at which patients need to be observed and the measures that need to be observed at each of those visits. And then we would attempt to collect that data. And EHR data is going to look very much not like that because there are going to be so many differences across patients in terms of their visit process and the tests that are performed at those visits. So because of that structure that I just described, and because EHR data were not collected according to any kind of a research protocol, most of the time when we go to use them to try to conduct a study, we're going to have to contend with missing data. I was just on a call with the FDA yesterday, actually, where they were saying, if anyone is trying to send data to the FDA seeking a label expansion or a new indication for a drug, they must include a plan for missing data. They are not required to include a plan to address any of the other problems that exist in EHR data, of which there are numerous, but missing data is so ubiquitous, you must have a missing data plan as part of your submission. So missing data are everywhere in EHR studies, and it's even difficult to get your head around what missingness means in the context of an EHR-based study. Because if we had designed the research protocol, if we had specified which data elements were intended to have been collected, then we could define missingness with respect to that. So we could say, you know, we need to see this patient once a month, and at each visit, here are the measures we'll collect. And to the extent that we don't observe that, that would constitute missing data. However, in the EHR, there's no prior specification of what should have been collected. So missingness is ultimately defined sort of post hoc, once we decide what purpose we're going to put the EHR data to in terms of our research and start to restructure the database to try to create the data elements that we need in order to conduct that research. This is particularly challenging in the context of trying to use EHR data for comparative effectiveness research. So, you know, throughout clinical medical research, clinical trials are, for good or for ill, generally considered to be the gold standard for estimating treatment efficacy. However, there are many reasons that clinical trials are not necessarily fully generalizable. They lack external validity. And in particular, they've been criticized for underrepresentation, in some cases even exclusion, of some patient populations. So the example that I'm going to be presenting today is in the context of oncology trials. And in oncology trials, it's been recognized and discussed for decades that racial and ethnic minorities are significantly underrepresented, and poor prognosis patients are also underrepresented and in many cases excluded from clinical trials. So the problem in the oncology context is once a treatment has been approved, it tends to be prescribed broadly. So even if poor prognosis patients were excluded or underrepresented in the trial, once the FDA has approved the treatment, clinicians are faced with the decision, should I give this treatment to my patient or not? So EHR data offer the opportunity to start to fill this gap. Once the treatment has been approved, we can take a look at the EHR data, take a look at the broad population of patients who are actually being treated with this approved therapy in routine practice, and estimate the real-world effectiveness of a treatment as opposed to the efficacy that was observed in the clinical trial. That's a desirable thing because it allows us to go beyond the more limited evidence that we have available from the trial, but there are many challenges associated with data issues in EHR data. And additionally, once we get to the point of trying to make treatment comparisons and actually estimate comparative effectiveness using EHR data, confounder control is going to be absolutely key because of the fact that there are going to be so many differences between patients receiving one treatment versus another in routine clinical care. So when I think about the many challenges that exist for trying to do comparative effectiveness research using EHR-based research, we can divide them into two buckets, those that constitute information bias and those that generate bias due to confounding. In terms of information bias, which is what most of my research focuses on, this arises due to the fact that the data elements that we observe are heterogeneous characterized in various ways using different tests, inconsistent across patients, and so on. So there's going to be a lot of measurement error and misclassification. There's a lot of missingness. Data elements are not necessarily defined in consistent ways across time, across providers, across healthcare systems, and so on. So a lot of information bias coming from those sorts of challenges with the data. Now, if we're trying to make treatment comparisons, we have additional problems that are introduced due to confounding. So confounder control using EHR data is quite challenging because we have limited information on many things that are potential confounders, including behavioral risk factors and social determinants of health, things like family history and symptoms, which may be recorded for some patients sometimes, but tend not to be systematically captured in EHR data, and things like disease severity. So if we want to use EHR data for comparative effectiveness research and come up with valid and generalizable results, we have to contend with both of these problems. We have the information bias problems, we have the confounding problems, and additionally, we have information bias essentially in our confounders. So we have measurement error, misclassification, missing data, et cetera, in the confounder variables themselves. So lots of challenges to deal with in order to realize the potential of EHR. So in the talk that I'm going to present today, I'm going to give you two examples of methodological investigations that were undertaken by my student Kylie and my postdoc Dan to investigate whether or not we could come up with better approaches to try to deal with the specific problem of missing data in confounder variables in EHR-based comparative effectiveness analyses. So this was a very practical, real world question motivated problem where we had an actual study that we were conducting using EHR data. We did what we felt was a reasonable analysis, trying to deal with the challenges in the data and use what we thought were best practices for a principled data analysis. But at the end of the day, we found that we felt that those approaches were a bit unsatisfactory, and we thought maybe some newer approaches might have benefits in terms of bias in the parameters that we were estimating. So I'm going to tell you about the motivating example, and then we'll take a look at those two methodological investigations. Oh, I accidentally just skipped ahead to much later in my talk. All right, let's go back to there. So the clinical question that motivated the work that I'm going to present today was, can immune checkpoint inhibitors, which throughout the talk I'm going to call immunotherapy, improve survival in patients with metastatic urothelial cancer? So this was a question that came from collaborators of mine in oncology and that we ultimately published in this paper in European Urology. This was a real-world clinical question that the urologic oncologists were faced with, and they were interested in answering it using EHR data. The specific EHR data that motivated the clinical investigation, and that I'm going to use as the basis for the methods investigations that I'm going to show you coming up, comes from the Flatiron Health EHR-based network. So this is a illustration of the geographic reach of the Flatiron Health EHR network. Flatiron is a collaboration amongst a very large number of cancer clinics throughout the United States. Flatiron accesses their EHR, provides structured data elements, as well as manual chart abstraction for a lot of data elements that aren't available in structured form, puts them all together into a big research database, and we're able to use it as academic researchers for free to answer this kind of clinical question. The specifics of the question that we were investigating was, we were in the setting of stage 4 urothelial cancer, investigated among patients treated at one of the oncology centers that were contributing to the Flatiron Health network. This is a very severe and poor prognosis disease. 1-year survival is only about 40% in this population. And at the time that we were conducting this investigation, several phase 2 trials had been conducted. So one-arm trials without a control group. So just looking at an intervention, in this case of immune checkpoint inhibitors. And those phase 2 trials had suggested that there was some benefit in terms of survival for these patients associated with treatment with immunotherapy. So on the basis of those uncontrolled trials, the FDA had approved immunotherapy. It went into routine clinical practice. Oncologists started prescribing this therapy broadly, but there was a real question about whether or not there actually was a benefit relative to the standard of care, which was chemotherapy. And in particular, there were a lot of patients who were underrepresented or even excluded from the clinical trials who were now being treated with immunotherapy. And there was really no benefit, there was really no evidence at this point in time that there was an actual benefit to treatment with immunotherapy versus the previous standard of care. So in the absence of evidence from a randomized trial, we decided to try to fill this gap using data from the Flatiron Health EHR database. This is one table from the results of that paper, just summarizing the overall survival comparisons between the patients in our Flatiron-derived cohort who were treated with immunotherapy versus chemotherapy. So the high-level conclusion that we came to was that immunotherapy was associated with poorer early outcomes, but better late outcomes. So if you take a look at this table, we have 12-month and 36-month overall survival in each of the two groups. You can see at 12 months, overall survival is lower in the immunotherapy group compared to the chemotherapy group. But by the time we get out to 36 months, overall survival is better in the immunotherapy group compared to the chemotherapy group. And in an inverse probability of treatment weighted Cox proportional hazards model, which we use to estimate the hazard ratio prior to 12 months and then separately after 12 months, we estimated that survival was poorer for patients treated with immunotherapy early on and then better later on. So this is very similar to other results that had previously been obtained looking at immunotherapy compared to chemotherapy in other populations. It's generally this phenomenon of crossing survival curves has generally been observed for immunotherapy, that it tends to have poor outcomes early, but then it has a long, durable response for patients who do well with immunotherapy treatment. So in this particular study, we were trying to deal with the fact that we know that there's confounding in which patients are treated with immunotherapy versus chemotherapy. So to address that, we're using inverse probability of treatment weighting. We also have a lot of missing data. So many of the confounder variables that we were interested in that went into computing those weights had missingness as part of them. And so we additionally addressed the missing data issue in this analysis using multiple imputation via mice. So in doing this analysis, we gave a lot of thought to these issues of confounding and also to the issues of missing data. And we tried to choose an approach that we felt was an established and justifiable research best practice. But despite feeling that we were doing our best, definitely at the end of the day, for me, concerns persisted that maybe we hadn't done an adequate job of addressing these challenges. And in specific, I was very concerned about the issue of missingness in one of the confounder variables. So a key confounder in this analysis and in many oncologic investigations is ECOG performance status. So ECOG performance status is a variable that summarizes the overall functional status of the patient. It's an ordinal variable that ranges from 0, meaning you don't have any functional limitations, you're doing just fine, all the way to 4, which means bedridden, you're really not able to do anything or take care of yourself. So in this metastatic urothelial carcinoma cohort, ECOG performance status was missing for about 35% of patients. So a pretty high level of missingness. And additionally, the clinical investigators raised a concern that not only was ECOG performance status missing, but it might be missing not at random. And the reason that they suspected that this might be missing not at random was that patients with very poor performance status, so performance status of 3 or 4, really should not receive treatment at all. And the clinicians were concerned that some of the cancer centers might have providers that were systematically not recording very poor performance status in order to justify continuing to treat those patients anyway. So in that case, the value of ECOG performance status itself would influence the missingness and would give rise to a missing not at random missingness mechanism. So grounded in this very practical real world setting, we had these open questions about how we could best analyze these data in the presence of a large amount of complex and potentially even MNAR missingness in a key confounder variable. So I'm going to show you the results from the two methodologic investigations that we undertook to investigate different aspects of this question. The first one just considers whether there are better approaches to multiple imputation in the context of EHR data beyond the mice approach, the kind of standard implementation of mice that we used in the urothelial paper. The specific things that we're going to try to address are there better approaches in the setting of very high levels of missingness, possibly complex patterns of missingness, and how do they perform in the setting of MNAR missingness, where we really don't expect that MI is going to be able to perform well. The second question that we investigated was whether there were alternative approaches that outperform multiple imputation, especially in the context of an inverse probability of treatment weighted analysis. So we sort of jumped straight to multiple imputation as a tried and true research practice, but since we're summarizing all of the confounder information into a propensity score, which we're then using in IPTW, maybe there's actually a better way to be doing the confounder control here, or a better way to be doing the accounting for missing data in this setting of using IPTW for confounder control. In particular, when we're in the setting of a very large EHR-based database, which sometimes can include hundreds of thousands or even millions of patients, multiple imputation might not be a computationally feasible option. So is there something more efficient that we could be doing? Okay, so taking the first of those questions, the first kind of standard tried and true approach that we had used for missing data, and that I'm going to use to compare the newer approaches in this example, is multiple imputation via chained equations. Multiple imputation via chained equations, or MICE, is really, really common. Essentially, we're going to specify a separate model for each variable that includes missingness. We'll fit that model using the complete cases, make predictions for the missing observations, then incorporate those predictions into new models for the other variables with missing data, update our predictions, update our models, update our predictions, update our models, et cetera, until convergence. This is very frequently used in analyses of EHR data. It allows us to specify a separate regression model for each variable in the model. So this is pretty flexible if we have variables that are of different types. So we have some biomarkers that are continuous. We have a lot of binary variables in the data set in the form of diagnosis codes, for instance. And we can customize each model to include just the relevant predictors if we'd like for each variable that has missingness. There are a couple limitations to this approach that we thought we might be able to address by using some newer imputation strategies. The first is just the process of model specification in this setting can be quite laborious. I think often when people picture using mice for multiple imputation, they kind of just picture you dump all of the predictor variables in, use all the variables to predict all of the other variables. It's pretty quick. But in fact, if you do it in a really thoughtful way, especially in the setting where you have derived variables, nonlinear terms, and potentially interactions, deciding how to incorporate those into your models and which models to include them in can be pretty complicated. Additionally, if you're using parametric models for any of those imputation models, the parametric models may provide a poor fit. They may be incorrectly specified. And in the setting of complex data like the EHR data, perhaps you're just not able to come up with a model that correctly or adequately fits the data. And then finally, like any MI approach, it's going to be computationally intensive for large EHR samples. So the first of the alternative strategies that I'm going to show you is multiple imputation with random forests. So in multiple imputation with random forests, we're going to stick with the mice strategy. So we're still going to use the same approach of specifying multiple conditional models for each feature in the data set with missingness. But rather than using a parametric model to make the predictions, to generate our imputations, instead we're going to fit a random forest to try to come up with a prediction for each of those features. So The rationale behind multiple imputation with random forests is really just that a random forest is potentially going to be more flexible. It's not going to require us to pre-specify the set of interactions that we want to consider or nonlinear terms that we want to consider. It's going to flexibly incorporate whichever ones the data suggests are needed in order to come up with a good imputation. There have been a few previous studies in the epidemiologic literature, in particular, looking at random forests as conditional models used in a mice context. And they found that random forests perform similarly to mice, to a standard parametric mice, when there weren't interactions or nonlinear terms. But when there were interactions that had not been included in the parametric mice model specification, using the random forests did outperform the traditional mice. It was able to pick up those interactions and more flexibly fit the data. The second and even newer approach that we took a look at was imputation via denoising autoencoders. So a denoising autoencoder is a neural network that attempts to predict the features from themselves. So the inputs into the autoencoder will be the features themselves. We'll then introduce some corruption and attempt to predict the original uncorrupted features from themselves. The specific implementation of denoising autoencoders that's been investigated in the past as a tool for imputation is what's called an overcomplete autoencoder. So in an overcomplete autoencoder, the number of nodes in the hidden layers of the network is actually larger than the number of inputs. So we start with a certain number of inputs, we corrupt them, and then as in any neural network, we're going to make a weighted combination of those nodes, apply a transformation, and predict a certain number of nodes within the hidden layer. We do that repeatedly for as many hidden layers as we choose to include in our model. And then at the final step, we try to take those weighted and transformed nodes and predict the original inputs. We're going to optimize the weights in the model by trying to minimize the mean squared error, comparing the inputs to the ultimate predicted outputs. So this approach is extremely flexible. This series of hidden nodes incorporating multiple inputs and outputs, even beyond the dimensionality of the original input vector, should allow for essentially arbitrary patterns among the missing data. This particular approach of using overcomplete autoencoders for the purpose of imputing missing data had been previously investigated in a couple papers in the informatics literature. And those papers had found that denoising autoencoders outperformed other more standard imputation approaches. One of the two papers that I cite here directly compared denoising autoencoders to mice, along with a few other approaches. The other one did not include mice as a comparator, but they both looked at kind of standard MI implementations. So past research had suggested that this might be a good approach for imputation. And in fact, those papers even indicated that denoising autoencoders could reduce bias in the setting of missing not at random missingness, which I have to tell you, when I read that in those papers, it evinced in me extreme skepticism. So the claim was denoising autoencoders could help us out even in the setting of missing not at random missingness. I found this dubious, but I wanted to see in a real world setting, could we actually achieve this benefit of using denoising autoencoders? There were a few limitations to the investigations that had previously been conducted from my perspective as a statistician working in a clinical epidemiology setting. The first was the way that these methods are typically evaluated in informatics and computer science is to apply them to various different standard data sets that exist. And most of the data sets that they had taken a look at were much larger, both in terms of number of observations and number of features than what we have access to in an oncology setting. So we wanted to evaluate performance in a smaller N and smaller P setting. Additionally, most of the machine learning and informatics literature evaluating imputation has really only looked at single imputation. There are some papers that explore multiple imputation, but it's much rarer. In many cases, they're just looking at single imputation. And finally, and most importantly from my perspective, the previous papers that had looked at denoising autoencoders really focused almost exclusively on evaluating performance in terms of looking at the mean squared error of the predicted missing features. So they're evaluating the models in terms of their ability to predict the features that were missing. I don't really care about the ability to predict the features that are missing, as long as at the end of the day, we get a good estimate of the parameter that we care about. So from my perspective, the performance of the model should be evaluated in terms of the bias and efficiency of the parameter estimate, in this case, for the hazard ratio of overall survival, not in terms of the predictive accuracy of the individual feature predictions. So we're going to undertake this investigation in the setting of plasmode simulation. So I'm not sure how broadly plasmode simulation is known, so I've provided a definition here. Plasmode simulation has been used first in the context of trying to recreate simulated data sets that captured the natural biologic variation observed in complex biological processes. It was subsequently adapted to the setting of EHR data, where researchers observed that EHR data are really complex. They're messy, there's a lot of stuff going on, there are many different variables that are correlated with each other in complicated ways. So if we conduct a simulation study by simulating individual features or even groups of several features that are correlated with each other, we end up with a data set that's pretty artificial and doesn't look much like the original data set. So in plasmode simulation, instead of simulating each feature from some known distribution, we're going to resample the covariate data from an original real EHR data set, in this case, our Flatiron Health EHR data set. We'll use the complete cases to estimate an outcome distribution. So in specific, we're going to estimate the baseline hazard for overall survival and also the baseline hazard for censoring, along with covariate effects relating each of the features to our outcome. And then we're going to take our sample with replacement from the complete data and use it to generate an outcome variable. So the objective here is to end up with covariate data that still reflects all of the complex relationships of the original data set, but in which the outcome has been simulated by us, so we know the true relationship between our covariates and our outcome. So that gives us a gold standard that we can compare our estimates from whatever kind of model that we're trying to evaluate to. But on the other hand, we're still preserving most of the original true structure of the data. So we're going to use plasmode simulation to generate simulated EHR data sets. We'll then introduce missingness and evaluate the performance of the alternative methods. We took a look at 3 different missingness mechanisms, and in all of the simulations that I'm going to show you, we did a similar thing, which is to generate our plasmode simulated data set. We then are going to introduce missingness into the ECOG performance status variable using one of our 3 missingness mechanisms, and then we'll introduce missingness into all of the other covariate data according to an MCAR, missing completely at random missingness mechanism. Our predictor variable immunotherapy and our outcome overall survival will assume to be complete. So we're not going to add any missingness to our primary exposure or our primary outcome. So first we'll have an MCAR missingness setting where both ECOG and all of the other covariate data in our data set are just have missingness introduced to them that's unrelated to any other of the features in the data set. We'll then look at a missing at random setting where missingness in ECOG performance status is going to be conditional on the exposure, the outcome, and the other covariate data that's observed in the data set. And then finally, we'll have a missing not at random scenario where the missingness in ECOG is allowed to depend on our exposure, our outcome, the other covariates, and the underlying value of ECOG itself. So for this first investigation, I'm going to show you the results of. What we're going to do is simulate the data in the way that I've just described. We're then going to fit a Cox proportional hazards model that includes adjustment for all of the covariates that we were interested in, including our key confounder ECOG performance status and our primary exposure of immunotherapy. We're going to compare multiple imputation using the standard mice approach, multiple imputation with random forests, or denoising autoencoders. And I'm also going to provide an estimate from what I might call the oracle approach, which is the estimate that we get if we don't add any missingness to the data. So it's kind of the best that we could do with the data that we have in hand. We're going to repeat this process across 1,000 plasmode simulations from the metastatic urothelial carcinoma dataset. We looked at bias, standard errors to try to get a sense of the efficiency of these approaches, and also confidence interval coverage probabilities. I'm only going to show you results for bias. I may make some comments about the other ones, but I think bias is really the most interesting one. So these are the results from our missing completely at random simulations. On the left, I'm showing bias in the parameter estimate, the hazard ratio for ECOG performance status, so for our confounder variable that had missingness in it. On the right, I'm showing the hazard ratio for our treatment effect, the immunotherapy hazard ratio. You can see under missing completely at random, everything works perfectly fine. If we use a complete case analysis, we lose efficiency, so it's not a great thing to do, especially under very high levels of missingness. But aside from that, all of our imputation approaches work just fine. They improve efficiency. They all are unbiased. When we move into the missing at random missingness setting is where we start to get into trouble. So under missing at random missingness, we see particularly as the amount of missingness in ECOG performance status increases, we get introduction of bias into our multiple imputation using random forests and multiple imputation using denoising autoencoders, whereas our mice multiple imputation continues to work just fine. Recall that there isn't any missingness in immunotherapy. The treatment indicator itself is assumed to be complete, but because of the fact that we are achieving incomplete confounder control, because we're not doing a great job of dealing with the missingness in ECOG, we additionally see some bias in the immunotherapy parameter estimate as well, particularly as we move to larger amounts of missingness for the random forest and the denoising autoencoder. And then when we move to the setting of missing not at random missingness, essentially all bets are off. I suspect it comes as no surprise to you. It did not come as a surprise to me that multiple imputation does not work very well in this setting. So we see bias in our complete case estimates. We see bias in all three of our multiple imputation estimates as well. So this study to me was kind of a cautionary tale that just because things are new and shiny does not necessarily mean that they work better than existing tried and true methods. So we found that there was no advantage of the machine learning methods for imputation compared to a standard parametric mice in the setting of an EHR-based CER study. We think that the reason that the random forest and the denoising autoencoder perform poorly, even under missing at random missingness, is that they are overfitting the data. So previous investigations had found that they're very good at predicting the individual missing observations, but there was less evaluation of how they performed in terms of controlling bias in downstream parameter estimates. And we think the denoising autoencoder in particular is so flexible that in the observed data, it's just tailoring the predictions to that data set really, really well, essentially overfitting the data and leading to poorer prediction in the observations with missingness. So we found that the machine learning methods didn't help. They actually seem to hurt under missing at random missingness. The use of the more flexible imputation approaches did not mitigate bias induced under MNAR missingness. The caveats here, of course, being that this is a simulation-based investigation. We specifically designed it to try to make it look like the real oncology EHR setting that we were in. So I think this is certainly informative about what we would expect and how we would expect these methods to perform in other similar Flatiron-based oncology EHR-based studies. Whether or not you would see the same thing in other contexts depends on how similar those contexts are to this one. But I think these results are probably generalizable across a lot of epidemiologic settings with similar sample sizes, similar numbers of features, and similar complexity in the amount of, in the missingness pattern. And then finally, my last bullet point on here, I think is probably like preaching to the choir for this audience, but for the broader audience of research practitioners, informaticians, computer scientists, et cetera, is just really important to evaluate the performance of missing data methods in terms of the performance of the downstream task that we're ultimately trying to achieve using the missing data, not in terms of the prediction accuracy of the individual missing data elements. And as we saw here, you can see a pretty big discrepancy between those two things, where you can be seemingly doing well at predicting the missing observations and yet do poorly at the downstream task of trying to estimate a hazard ratio. So the second investigation that we undertook essentially asked the question of whether or not we should even be doing this multiple imputation based method to address missingness, or whether there's an alternative that's possibly more computationally efficient. So one of the things that I think is really important to reflect on as you're choosing a strategy for dealing with missing data is whether it makes more sense to conceive of the problem at hand as a missing data problem or a measurement error problem. So in EHR-based research, the fact that confounder data are sporadically available, there's a lot of missingness, as I mentioned earlier, in things like family history and symptom severity. Typically, people think of that as a missing data problem, but we could alternatively conceive of it as a measurement error problem. So although the gold standard confounder information that we wish we had is often not available, there's a lot of proxy information in the form of diagnosis codes, prescriptions, and utilization information. So if we think of those codes and additional information as being proxies, imperfect surrogates for the gold standard confounded information that we wish we had, then we could alternatively conceive of this as a measurement error problem. A couple years ago now, I guess my student, Joanna Harton, had conducted an investigation where we had a very similar question. We were conducting comparative effectiveness research using EHR derived data, and we wanted to incorporate a propensity score into the analysis. If some of the variables contributing to the propensity score have missingness in them, that results in a missing propensity score value. And Joanna had investigated this question. Rather than treating this as a missing data problem, can we treat this as a measurement error problem and use regression calibration to calibrate the estimates that are adjusted for that propensity score that's only available for some patients? In the specific case of the Harton 2021 paper, she had used propensity score adjustment in a multivariable model. And this is somewhat limited, and we were interested in going beyond this setting because propensity score adjustment in a multivariable model is kind of a suboptimal way to use a propensity score. It's dependent on an assumption that we've correctly specified the functional form of the relationship between the propensity score and the outcome. It's not a commonly used approach in comparative effectiveness research. People more frequently do matching or weighting. And additionally, she hadn't looked at a head-to-head comparison between missing data and measurement error approaches. She had only compared alternative measurement error approaches. So in this setting, what we would like to do is take the propensity score, a fundamental tool for causal inference in observational data, and treat the propensity score as a dimension reduction tool that's taken all the information that we need about the confounders, reduced it down to a single dimension, but that single dimension now has missingness in it. So our propensity score, I'm going to denote with E of X. That's just going to be our probability that you're in the intervention group. We can think of that in the urothelial cancer setting as the immunotherapy group, conditional on your vector of covariates. So we've taken this vector of covariates and summarized it down to the level of a single number, E of X. E of X can be estimated in all sorts of different ways. In the IPTW analysis in the real study that we had conducted, we used superlearner to estimate E of X. So we're trying to use a more flexible approach. Often people use logistic regression, but you can kind of use supervised learning strategy of your choice. So the situation that we have, this is not real patient data, but this is a representation of what our patient data sort of look like in the urothelial cancer setting. We have a bunch of different covariates that we think are potentially associated with treatment assignment. So we have this set of covariates X. We would like to use them to construct a propensity score E of X. However, some of the variables that contribute to that propensity score have missingness in them. So any individual who has missingness in any of the covariates that contribute to their propensity score is going to end up with a missing propensity score. Therefore, we could take a look at a reduced set of covariates, here denoted X star, and we could construct a proxy propensity score. So E of X star is a propensity score that's only based on the covariates that don't have any missingness. So that propensity score is going to be complete for everybody. We could then take a look at our original propensity score E of X, and we could think of it as being a variable that has missingness in it. And we could therefore try to impute the missing data in order to obtain a E of X for everybody. Or we could think of the individuals who had complete covariate data as a validation sample who are contributing information on this gold standard propensity score. And we could look at the relationship between the gold standard propensity score E of X and our surrogate propensity score E of X star, and use the information about the relationship between those two things to carry out a regression calibration for E of X. So this idea of directly carrying out regression calibration on a propensity score is called propensity score calibration. It was originally proposed back in 2007. It proceeds pretty much as I just described or summarized. We're going to predict a propensity score E hat of X based on complete covariate information, all of the confounders that we're worried about. We're also going to estimate what I'll call an error-prone propensity score based only on those covariates X star that don't have any missingness. We then fit a calibration model by regressing the gold standard propensity score on the error-prone propensity score and the treatment indicator for everybody who has complete data. And then we use that calibration model to generate predictions for the true propensity score, the gold standard propensity score, for everyone who had it missing. We can then incorporate that imputed gold standard propensity score into our inverse probability of treatment weighted outcome models. So we're going to investigate the relative performance of propensity score calibration in comparison to a multiple imputation using mice, using a very similar plasmode simulation-based approach to what I described for the previous study. So we're going to use the same approach to simulating the missingness, same sorts of patterns of missingness and looking at various degrees of missingness. We're going to introduce the 3 different missingness mechanisms into ECOG performance status, and then missing completely at random missingness in other covariates. In this analysis, we assumed that just 3 predictor variables had complete information for everybody. So our error-prone propensity score will be based on just gender, surgery, and age. And all of the other covariates were allowed to have missing data. And then I'm going to compare performance of a complete case strategy that just drops everybody with a missing propensity score, multiple imputation, where we impute the underlying covariates, and a propensity score calibration. And again, I'm just going to present the results for bias. So here I'm showing the results for just one strength of effect for the relationship between immunotherapy and overall survival. And in this setting, because we're using IPTW, the only parameter estimate that we are generating is the hazard ratio for the relationship between immunotherapy and overall survival. So in this case, there is no parameter estimate, for instance, for the ECOG performance status effect. The main takeaway that I get from all of these simulations is the complete case approach, not surprisingly, is inefficient. When the data are missing at random or missing not at random, we start to see bias, especially under high levels of missingness. We can correct and remove most of that bias using either multiple imputation or propensity score calibration, and the 2 approaches perform basically indistinguishably. So in terms of bias, in terms of efficiency, and also in terms of the confidence interval coverage probabilities that I'm not showing you, but you have to take my word for, the performance is essentially equivalent. So both approaches perform very well here. In this setting, we do see the missing data methods with the multiple imputation and propensity score calibration performing pretty well, even under missing not at random missingness. I don't want to pretend that I think that that is a feature of the approaches that we use. I think it's a feature of the specific way that we introduce the missing not at random missingness. But I don't think that it's a magic result due to using IPTW as opposed to the previous analysis that used regression adjustment. And I can go into more detail about why I think that is here, but the main takeaway for me is that multiple imputation and propensity score calibration were essentially equivalent. The only way in which they really noticeably differed was in terms of computational efficiency. So in the lower right hand of the slide, I have a little table inset here that just gives the runtime for the computer that was performing the simulations for the 3 different analyses under one of the missingness mechanisms and across proportions of missingness. Not surprisingly, the complete case analysis is really quick. It gets quicker the more missing data you have because your sample size gets smaller and smaller. Multiple imputation, and here we were using 10 imputations per simulation. Multiple imputation takes longer, not surprisingly. The propensity score calibration takes only about the same amount of time as the original complete case analysis. So in this setting where we had a sample size of about 3,000, it would not be infeasible to use multiple imputation. Waiting around about 10 minutes for your results is not really a big deal. But if we had a larger data set that had hundreds of thousands or millions of patients, there definitely would be an advantage to using propensity score calibration. So in terms of what we learned from this investigation, both the multiple imputation and propensity score calibration performed well in terms of controlling bias. The propensity score calibration was substantially more computationally efficient. But an important thing to keep in mind is how well propensity score calibration works is going to depend on how many variables you can incorporate into that complete propensity score based on the error, the complete data or error-prone or proxy propensity score. So in the example that I showed, it had 3 variables in it that didn't have missingness. As you have more and more missingness in various covariates, you end up with fewer and fewer variables that can be part of that error-prone propensity score. And so, just like the previous simulation, this is a simulation-based investigation. Results in any other context will resemble these results to the extent that that context resembles this simulation. So to wrap up, and give you a few high-level thoughts of what I kind of conclude from these studies. The first is in terms of comparing the evidence that we can generate from real-world data to the evidence that we can generate from randomized clinical trials. This is something that has received a lot of interest, especially over the past 2 years of the COVID-19 pandemic. So people have really embraced using observational data, but there's also been a lot of concern that we potentially going to come to erroneous conclusions due to the kinds of data issues and confounding issues that I mentioned earlier. I would argue that we shouldn't think of this as potentially using real-world evidence to replace randomized clinical trials, but to supplement or complement or fill in the gaps in what we can do in an RCT. So on this slide, on the left, I'm showing you the investigation that we conducted that was published in 2019 based on the Flatiron Health EHR data. I'm showing you the Kaplan-Meier curves for immunotherapy in blue and the carboplatin-based chemotherapy in red. About 7 months later, the results of the phase 3 randomized trial investigating a similar clinical question were published, and that's the curve that I have on the right. The overall conclusion from these 2 studies is really, really similar. Both found that there was an early benefit of chemotherapy and a late benefit of immunotherapy. Both found that if you didn't account for that crossing of the hazard ratios, there was no global effect. No global benefit of immunotherapy versus chemotherapy. So essentially what the real world study provided was evidence to answer a timely clinical question. The drug was on the market, providers needed to make a decision whether or not they should be using it, especially in patient populations that had been underrepresented in the trial. And so we provided information to fill the gaps, to answer that question until the trial could be completed. I know there's a lot of concern about biased results being generated by real-world studies, and I think it's an important issue, but I also think it's important to remember that science is defined by a body of evidence, not any single study. So we should be doing the very best that we can to come up with rigorous, valid evidence for any given question, but we shouldn't consider any one study to be the be-all, end-all of evidence for that question. So I think using real-world data to complement randomized clinical trials makes a lot of sense. We should never expect that they're going to completely replace trials, because trials are able to achieve confounder control in a way that observational studies will always struggle with. At the same time, observational studies and real-world data will allow us to reach populations that trials tend to exclude. So I think the first couple of points on here, just repeat what I just said, that EHR data give us the opportunity to investigate questions that it would be infeasible or untimely to investigate using clinical trials. And in particular, I think their ability to allow us to extend inference to underrepresented populations is particularly important. However, there are important EHR data quality issues to consider, and especially in the setting of comparative effectiveness research, which is extra challenging because of the added issues of confounding. There's been a lot of focus on how we achieve confounder control, how we avoid bias due to confounding, and relatively less emphasis on information bias. Both are super important concerns in this setting. There are novel approaches out there that definitely bear investigation that I think we should be embracing and studying, such as the machine learning approaches that I discussed in my first example. But new things are not always better, and just because something is new, we should not assume that that represents a panacea that's going to fix all of our problems. So I would definitely trust but verify any proposed new method that's going to solve all of my problems. And finally, doing this kind of practical methods investigation, I think, is really important, just to make sure that the methods that we're using in real-world studies actually achieve the promise and allow us to realize the potential of EHR data. We need to be constantly pushing the boundary forward of what the best research practices are for investigating these urgent clinical and public health questions. And I think these kinds of practical methods investigations can fill in those gaps. So I'm going to end there. I would like to acknowledge again the contributions of Kylie and Dan, whose work this really was, as well as the financial support of NIH. I have this slide that is very dense with references that I'm assuming, I guess you could screen cap it real quick, but I'm happy to share my slides if anyone's interested in any of the references that I presented to the various multiple imputation approaches, propensity score calibration, our urothelial paper, et cetera. So I've got this for you if you would like me to share it with you. And I will end there.
Thank you so much. Are there any questions? I think there was one in the chat from Jenka. Do you want to ask, or do you want me to read it?
Yeah, I can ask. Can you hear me?
Yep.
Yeah. Thanks, Jean. And thanks, Rebecca, for the great talk. I think we learned a lot. And I just have a technical question. I wonder, in your regression calibration approach, how did you get the E hat X, where the X is the entire set of the cohorts you're considering? I wonder, do you make any assumptions about that E hat X being, say, convergent to the true propensity score, or actually don't care? And the regression calibration approach will actually fix that. So maybe that's something maybe I've missed something, or could you please explain that aspect?
Yeah, that's a great question. And no, I don't think that you missed anything. I don't think that the propensity score calibration would save you if E hat of X is biased for E of X. So if your propensity score model is not a good model, if you've misspecified the propensity score model, for instance, I don't think anything about trying to do the propensity score calibration, trying to predict E hat of X from E hat of X star is going to solve that problem. So, that kind of goes to the issue of trying to use a more flexible model for the propensity score calibration. In the example that I showed, it's just based on using logistic regression. There are certainly more flexible approaches that would potentially get around the problem of having a misspecified propensity score model, but no, I don't think the propensity score calibration would help out in that case.
I see, thanks.
Rod, I see your hand.
Thank you, and thank you, Rebecca. It was a great talk. I really liked it. I like a lot about what you said, particularly a pet peeve of mine, which is the machine learning people looking at mean squared error of prediction rather than what the inference is on the actual parameter you're interested in. I think that's an important point. I had a lot of thoughts that came up, and I captured your references at the end, which could be useful. In the first simulation, are you assuming that that if you have complete data on that confounder, then you don't really have any confounding bias? In other words, that actually removes the effect of the confounding.
Yes.
Yeah, right.
Yes, we are, because the way that we did the simulation, we're assuming that we've captured all the confounders, we have all the confounder data we need. Yeah.
Just a comment on a lot of the machine learning methods that I've seen include indicators for the missing values as predictors, and that you can show that that's actually does make an assumption of a certain kind of a missing not at random assumption, a particular missing not at random assumption, which is different from what chained equation stuff does. So I think that's actually quite an interesting issue. And of course, there's an infinite number of missing not at random mechanisms you could have. So it's very hard to capture what the real one is in a simulation study. I think you did a nice job, actually. I think it's very difficult to do these simulations, and it sounds to me like what you were doing was better than what a lot of alternatives that you could see. I just want to make a general comment, and that is that you can view all of these problems, confounding bias, measurement error, and missing data, and deal with them all by multiple imputation. So I have this with Mike Elliott and a student of ours. We did this method PenComp, which penalized I've forgotten what it's called now. It's terrible when you forget your own acronyms, right? Penalized spline for compensity for treatment comparisons that imputes the outcomes under the alternative treatment, but also uses the propensity in the model as a spline, which captures which is sort of different from the weighting approach to that. And then the measurement error you can also deal with as a missing data problem. So there is a kind of unified way of looking at all these problems, I think, which is quite useful. Where there are obviously problems in trying to do this with large data sets like this, but I think conceptually that's kind of useful. That's why I like multiple imputation as an overall conceptual thing, because I think you can sort of conceptually can handle all of these problems.
Yeah, thanks for that. That sounds really interesting. I like unifying theories of things, so I'll definitely look for that paper.
I can send you some of these references if you're interested. So
yeah, that would be great.
Are there any other questions? I had just a technical question about would you be willing to go back to the slide where you were showing the comparison of the bias in the imputed values versus the bias in the parameter that you were estimating?
Like
yeah. So the intervals around the points, is that your simulation variation?
Mm-hmm.
Or okay. So the random forest and the autoencoder are failing at recovering the data also. They have bias in both the parameter and in recovering the data.
Presumably. So these are both parameters. So this isn't like mean squared error of the prediction. This is bias in the hazard ratio for the confounder variable.
Okay. I misinterpreted what the left plot was.
But my assumption is that the reason that that's happening is because they are not performing well in terms of the prediction. I mean, maybe there's another, that was the reason that occurred to me as, why you're getting a biased parameter estimate here.
Okay, yeah, so you had a theory that they're overfitting, that maybe actually they're doing a better mean squared error job of recovering the missing data.
So
did you look into that, or?
No, we didn't look into that actually. So my theory is that if you looked at the mean squared error for the predictions in the complete cases, that's essentially what it's optimizing. And I'm making an assumption that I think it's doing really well, but then when you make the predictions for the missing cases, it's not doing so well. But that's an empirical question because we simulated complete data. So we could take a look at that.
Yeah, that would be cool. That would be a cool result to see.
Yes, we should probably do that. So this particular paper is currently under review, I think at Epidemiology, but I can imagine a reviewer asking that question or on a future submission elsewhere. I think that would be a good thing to add.
Thanks.
Yeah, thank you.
You didn't say very much about confidence coverage. I don't know. Do you have any? Is there any quick things you could say about that?
It was generally close to nominal. It degraded a bit as you got to the high levels of missingness, the 50% and 70% missingness. And it was in this simulation, there was more bias in the denoising autoencoders and the confidence interval coverage was worse. In the other simulation with the propensity score calibration, when you got up to the scenario with 70% missingness, the confidence interval coverage for both the multiple imputation and the calibration dropped down to in the ballpark of 90% at the high level of missingness, and it was very similar between the two approaches, which
so if you have the actual data set where there's a lot of large sample size, you kind of expect a relatively small bias to translate into poor coverage. Right.
Yeah. Hi, Brahmar.
Hi, Rebecca. How are you? Thanks for a fantastic talk. And the takeaway message, particularly for our students, is that if you see something jazzy in the machine learning world, don't just accept it that this is going to give you jazzy results. So thank you for that message. I had two questions. One, maybe I have missed it. One is that the visit times, the visit process itself is incredibly informative, right? So because I am seeing a marker because I'm sick, because it was ordered, or I have healthcare access, it's a multitude of factors in terms of patient and provider level variables. So did that observation process, explicit modeling of TIJ play any role into this? No.
That's an issue that we've thought about in other contexts. In this study, we didn't explicitly think about it. Our outcome here of overall survival, we're sort of just making the assumption that it's well captured. You can press on that assumption a little bit, and it's not actually as great as one might expect, but it's, here we're just assuming that it's pretty good. And we're also assuming that we're just simulating all of the covariates and treating them all as baseline covariates. So we're collapsing all of that longitudinal information from the EHR into a single value. I mean, in fact, as you said, the visit process is complicated, particularly for ECOG performance status. That's something that we've looked at before because it's measured repeatedly at varying frequencies across patients. And so in the real study, the real clinical investigation, we pulled the value that was closest to the start of treatment, trying not to go back too far in time or forward too far in time. But, you know, in practice, certain patients will have it observed closer to start of treatment than others. And that is another potential source of bias as well, probably sort of a measurement error problem, potentially a differential measurement error problem where certain patients are more likely to have more proximal capture than others.
And the second question is selection bias, right? So you are handling the missing data, but who is in your study? Who is in the CHR? Who is included? And how does it generalize to the target population of inference? So how do we know about that?
Yeah, that's a great question. In the Flatiron Health database, I actually feel pretty good about the generalizability of that database because it is based predominantly on community cancer clinics, as well as a few academic clinics, but it's large, nationally representative. In this particular setting of metastatic cancer, at community cancer clinics, I think we're doing a pretty good job of capturing a representative population of cancer patients. You know, if we were in a different setting, if we were only using pen data, for instance, be a lot more concerned about that. So, you know, if you were conducting a study similar to the one that I've described, but you're doing it at single institution using data from a big academic medical center, you might need to be concerned about the selection bias issue on top of all these other issues that we're dealing with. And definitely, I feel like conducting this work in oncology, and especially in advanced cancer care, you're more likely to see all of the patients that represent the universe of patients in your data set. You know, there are a lot of conditions that are undertreated. And so the patients who turn up, have insurance, are able to seek care, are not necessarily representative. So yeah, definitely thinking about the selection bias issue additionally needs to be layered on top of some of these. Yeah,
cancer is actually a good outcome to look at in EHR because there is not so much misclassification and also undercoverage. So
yeah, and you know, it's captured pretty well. You have like a relatively captive population. So one of the things that I really worry about with EHR-based studies is the fragmentation of the information ecosystem. So, you know, we only see patients treated in this healthcare system. With cancer patients, especially an advanced cancer population, I don't expect there to be too much movement outside of network, but you know, there may be some. The other thing that's a challenge with Flatiron data is it's an oncology EHR. So the information that we are looking at is information that was recorded in the oncology EHR. If we are interested in, for instance, controlling for comorbidities, and those comorbidities are not directly related to cancer treatment, the oncologists just don't record them. So, you know, there are pros and cons to all these different data sources. Ideally, we would have a more complete, more holistic picture of what's going on with the patients. But here, I do think we have good capture of their cancer care, at least. Outside of cancer care, not so good.
Yeah. Thank you so much.
Great. If there's no more questions, I guess we will wrap up. If you have questions, now's your chance.
You can also always feel free to email me. I'm dangerously responsive on email.
Okay. All right. Nice to see everybody. We will see you next week.
Bye. Thank you.
Thanks so much, Rebecca.